Ouais. Est-ce que Ange est en ligne avec nous? Pas encore? Pardon.
Ange Enzo, c'est bon, je l'ai. Il est tout en bas. Donc, vous pouvez lui parler, lui demander si
Oui.
éventuellement de remettre son micro en route.
Non, Ange, tu es en ligne. Tu nous entends? Apparemment, non. Oui, c'est bon. OK, parfait. D'accord. Très bien. Très bien. Donc, on va pouvoir commencer. Bonjour, bonjour à tous. Bonjour, Riham. Bonjour, Ange. Est-ce que tout va bien?
Oui, là, je vous entends. Tout va bien. Merci.
Parfait, parfait, parfait. D'accord. Donc, bonjour. Je m'appelle Deborah Jones. Je suis directrice de recherche à l'Institut Charles Gard à Montpellier et j'ai l'honneur de présider ce jury de soutenance de thèse de Riham KANAAN. Et je vais commencer tout d'abord par présenter les différents membres du jury. D'abord, les deux rapporteurs. Donc, nous avons en ligne le professeur Ange Nijou, qui est professeur à IMT Mine d'Albi. À mes côtés, le monsieur Loïc Casso, maître de conférence ICMO, Université de Paris-Saclay. Les examinateurs, donc le professeur Gaël Maranzana, ici à ma gauche, examinateur, donc professeur à l'Université de Lorraine. Monsieur Julian Durst, qui est ingénieur à la société Symbio. Moi-même, Deborah Jones, et donc les deux personnes qui ont suivi de plus près ce travail, donc Christian Bourget et Pedro Afonso Nobrega. Voilà. Donc, on va nous asseoir. Et je vais inviter donc Riham à présenter ses travaux dans une 45 minutes. Voilà.
Thank you. Welcome, everyone. Thank you for being here to attend the presentation of my PhD work, which concerns the hydrogen recovery from ammonia for positioning the electrolysis route. The use of low-carbon hydrogen in the industrial and the transportation sector is necessary for the carbon dioxide emissions reduction. This, however, requires the easy access to cheap low-carbon hydrogen. This hydrogen that comes from countries in the world where the renewable energy is cheap and abundant, such as Australia, North Africa, and the Middle East. This, however, introduces the need for the long-distance transportation of hydrogen using ships. Ça marche pas très bien. Since the liquid form is the most adapted for the long-distance transportation, liquid hydrogen technology was investigated. This technology takes place at a temperature of -253 degrees C and has the disadvantages of the high energy requirement in addition to the problem of boil-off.
Quand tu repenses aux souvenirs, des trucs que vous avez fait ensemble, toujours ce petit truc de c'est vrai que c'était pas mal.
Pour les personnes en ligne, est-ce que vous pouvez éteindre vos micros, s'il vous plaît?
Tu vois, c'est un truc dans lequel il faut
s'investir. Ça marche pas très bien.
Ça demande de l'investissement.
Moi, je suis un peu pareil, mais je n'ai pas ce truc de je ne veux pas être. J'ai plus ce truc de je ne cherche pas.
Mais c'est un peu ça, c'est je cherche pas à être. Et de toute manière, je pense que même si je serais très sur arriver à. Genre, c'est peut-être une mauvaise vie, tu vois. Et que ça me rendrait triste, en fait, d'être en couple avec quelqu'un.
The first effective liquid hydrogen shipment took place in 2022 between Australia and Japan. However, it was associated with high hydrogen shipping costs. For this reason, alternative liquid storage media were investigated, such as liquid organic hydrogen carriers and ammonia. According to the International Energy Agency, ammonia is expected to become, by 2030, the cheapest option to transport hydrogen in the liquid form. Ammonia can be produced from the reaction between nitrogen and hydrogen. Why ammonia? Because it has a high hydrogen gravimetric content, it's present in liquid form under mild conditions, and it has a well-developed infrastructure for its distribution and transportation. For this specific reason, 80% of the announced hydrogen trade projects prioritize ammonia as a liquid hydrogen carrier. Ammonia, however, is highly volatile and could be toxic depending on the concentration and the exposure time. This means that this molecule should be carefully handled in order to avoid ammonia accidental spills. The use of ammonia as a liquid hydrogen carrier requires the conversion of hydrogen into ammonia at the point of hydrogen production, transportation as liquid ammonia, and the recovery of hydrogen back at the arriving import terminal or at the point of use. Different ammonia reconversion technologies are available, and these include the conventional thermal decomposition technologies. It is the most mature with the technology readiness level between 7 and 9. In this sense, large-scale ammonia crackers are already being constructed and are expected to operate before the end of 2024 in different places such as Germany and Netherlands. Other less mature technologies are also available, such as electrolysis, photocatalysis, and plasma-based technologies, with TRL less than 4. In this thesis, we are interested in the electrolysis route because it is the most mature among the non-conventional technologies. Hence, the objectives of this thesis are, first, to position the ammonia electrolysis route with respect to the conventional thermal decomposition technologies by conducting a techno-economic assessment. And then, in an attempt to reduce the costs associated with the ammonia electrolysis route, the objectives are to deepen knowledge on this route through experimental investigations. For this reason, this presentation is going to be divided into two parts. The first, which concerns the techno-economic assessment, where the different process configurations will be described, a kinetic and a physical model will be developed, an economic study will be established, and finally, the results will be presented. In the second part, which concerns AEM ammonia electrolysis, we will design a hydrogen test bench. After that, we will present the methods for the preparation of the anodes and the MEA, and finally present the results of the MEA evaluation. To start with the first part, in order to achieve the objectives of the techno-economic assessment, we consider two reconversion technologies for the thermal decomposition route, consisting in a fixed bed and a membrane reactor technology. As for the electrochemical route, we consider alkaline electrolysis because it is the most mature electrolysis technology available. Different process scales were also considered, such as a heavy-duty truck producing on board 22 kilograms of hydrogen per day and operating 80% of the time, a medium-sized hydrogen refueling station with a capacity of 1,000 kilograms of hydrogen per day, operating 50% of the time, an ammonia import terminal with a capacity of 1,500 tons of ammonia per year, operating 90% of the time. Now we will start by identifying the different equipment involved in the different ammonia reconversion technologies. Ammonia thermal decomposition can take place in a fixed bed reactor, which is the conventional high temperature reactor. In this process, ammonia is introduced and is preheated in a recovery heat exchanger before being introduced into the main reactor, operating at a temperature of 650 degrees C, pressure of 1 atmosphere, and in the presence of a commercially available ruthenium-based catalyst. The effluent of this reactor is sent into purification unit, pressure swing adsorption, in order to recover pure hydrogen. Heat integration was used in order to provide the energy requirement of the system, which means that it comes by burning the waste stream of the PSA unit and part of the ammonia feedstock when needed. Assuming nitrogen restrictions on the nitrogen oxides emissions, a denitrification unit is added downstream the furnace. In a membrane reactor technology, the fixed bed is replaced by a membrane reactor where the reaction and the purification section take place at the same time. This reactor operates at a pressure of 10 atmosphere ensured by the compressor at a maximum temperature of 600 degrees C, after which the materials of the membrane start to degrade, and in the presence of a commercially available ruthenium-based catalyst. Heat integration was used in order to provide the energy requirement of the system. Only in the case where ammonia is stored in the refrigerated form, an evaporator is added before the compressor inlet. Now we will develop a kinetic model for the reactors as well as a physical model for all the other equipment. The goal is to dimension these equipment and have an idea about the material and the energy requirements to be able to calculate the associated costs. The thermal decomposition reactors were modeled as packed bed reactors having isothermal temperature, high gaseous flow rate, ideal mixing, and homogeneous conditions in the radial flow. The model was developed based on the mass and heat balance equations while adopting a specific kinetic rate law depending on the chosen catalyst, which is ruthenium supported on alumina. This is because we could find kinetic data for this catalyst in the literature, which was not the case for other catalysts. The other equipments were also modeled based on their physical characteristic equations. Taking the example of a heat exchanger, it is possible to calculate the surface area based on heat balance equations. As for the electrochemical route, aqueous ammonia solution is introduced into the electrolysis stack. This stack operates at a temperature of 25 degrees C, pressure of 1 atmosphere, in the presence of platinum-based electrodes and a highly concentrated alkaline electrolyte. The effluent of the stack is sent into a purification unit in order to recover pure hydrogen. This stack is modeled as a group of identical cells connected in series with uniform fluid flow, homogeneous temperature, and while neglecting mass transport limitations. The model was developed based on the Faraday law. Now it's time to establish the economic study. The total costs associated with any process involve the capital expenditures, which include the cost of equipment and installation, the cost of land, and the cost of piping, as well as the operating expenditures, which include the cost of electricity, feedstock, catalyst, fuel, and maintenance. These allow the calculation of the levelized cost of hydrogen by defining an interest rate and an equipment lifetime. Another interesting parameter also is the reconversion cost, which represents the levelized cost of hydrogen, excluding the cost of the feedstock. The capex of any equipment can be calculated based on a reference equipment having a reference cost at a specific design parameter, using this power law. Taking the example of a heat exchanger, this design parameter is the surface area. These values were also corrected based on the chemical engineering plant cost index in order to adjust for variations in the costs of plant construction from one period to another. In order to determine the levelized cost of hydrogen nowadays, we define a current scenario parameters. This includes a capex of an ammonia electrolyzer of $1,500 per kilowatt for small-scale applications with 20% reductions for the large-scale applications. Although commercial ammonia electrolyzers do not really exist, we consider this cost to be the same as that for alkaline water electrolyzers, since similar components are expected to be in these electrolyzers, with the only difference of the catalyst material whose cost was already accounted for in the operating costs. We also consider renewable ammonia with a price of $1,000 per kilogram of ammonia and electricity price coming from the grid with $98 per megawatt hour. Now for the results. The levelized cost of hydrogen was calculated for all the reconversion technologies and the process scales. These values vary between 7.7 for a membrane reactor in an import terminal to 11.4 for a fixed bed reactor on board a truck. For the thermal decomposition technologies, the levelized cost of hydrogen calculated lie in the range of renewable hydrogen prices calculated by the International Energy Agency. On board the truck, the prices of hydrogen produced seem to be too expensive to be competitive with any hydrogen produced from other sources. Although electrolysis seems to be the least expensive, however, it seems to be unrealistic for the moment to install an electrolyzer on board a vehicle, and we only considered this case study to have rough estimates about the costs. The reconversion costs were also calculated to be between 0.7 and 3.9 depending on the technology and the process scale. For the thermal decomposition technologies and in large-scale applications, these values were conforming to those calculated by the International Energy Agency. However, this was not the case for electrolysis due to the high capital cost of the technology itself. Another interesting parameter was the energy efficiency of the system. Thermal decomposition routes provided higher energy efficiency despite their higher thermal power requirement. This is because heat integration was used in these processes. In addition, higher electrical power is observed for the electrolysis route with 13 kilowatt-hour per kilogram compared to 2 kilowatt-hour per kilogram, for example, for a fixed bed reactor. Among the thermal decomposition technologies, the highest efficiency was obtained for a membrane reactor due to the lower temperature requirement resulting in lower fuel consumption. With the variation in the prices of the electricity equipment and commodities in the future, the levelized cost of hydrogen will be impacted. For this, we define a future scenario parameters consisting in reduction in the capex of the ammonia electrolyzers, which could be attributed to the increase in the capacity of the installed electrolyzers in the future, as well as their mass production due to the automation of the process. As a consequence of a reduction of the electrolyzer capex, the renewable ammonia price would also decrease. The price of the electricity from the grid is expected to face a slight increase due to the increase in the share of the renewables in the future, which will impact the flexibility of the energy system. And finally, we consider 20% reductions in the capex of the membrane reactor due to possible improvements that could take place in this technology in the future. Taking the case of a hydrogen refueling station, a future case scenario analysis results in a reduction in the levelized cost of hydrogen to less than $8 per kilogram. This conclusion was valid for all the process scales. As for the reconversion costs, a slight decrease was faced for the thermal decomposition technologies, mainly due to the decrease in the prices of renewable ammonia, which will decrease the fuel operating cost. As for the electrolysis, this reduction in the reconversion cost was more pronounced due to the huge reduction in the capex of ammonia electrolyzers. These reconversion costs were used in order to assess the techno-economic feasibility of the marine hydrogen transportation. For this, we take the specific case of transporting hydrogen in the liquid form from the port of Casablanca in Morocco to the port of Marseille in France. We compare two different technologies, liquid hydrogen transportation and storage in ammonia. The International Energy Agency calculated the cost of liquefaction, shipping as liquid hydrogen while considering the losses, and the cost of regasification. At the end, a total cost of $3 per kilogram of hydrogen was obtained for this technology. As for storage inside ammonia, the International Energy Agency also calculated the cost of conversion and shipping as liquid ammonia. The reconversion cost, however, will depend on the technology used and on the process scale. When considering the case of an import terminal, we obtained these values. At the end, a total cost of $1.7 to $3.5 per kilogram was obtained for this technology. This means that using ammonia as a liquid hydrogen carrier could be cost competitive to liquid hydrogen transportation in the future when ammonia is reconverted in an import terminal. At the end of the first part, where we conducted a techno-economic assessment for the different process scales and reconversion technologies, we could say that in a current scenario parameter, the cheapest option to reconvert ammonia for large-scale applications is using a membrane reactor technology. A future case scenario results in a reduction of the levelized cost of hydrogen to less than $8 per kilogram. And using ammonia as a liquid hydrogen carrier could be competitive to liquid hydrogen transportation in the future. All these results were published in the prestigious journal Renewable and Sustainable Energy Reviews. The lack of sufficient information to build a precise kinetic model for the ammonia electrolysis route urged the need to obtain our own data. For this, we select this route for further experimental investigations. Specifically, we select anion exchange membrane electrolysis because compared to the conventional alkaline electrolysis, it provides different advantages such as the higher operating current densities, the more compact system, and the higher hydrogen purity. In addition, this technology is less mature, which provides room for further development and innovation. In AEM ammonia electrolysis, the ammonia oxidation reaction takes place at the anode and the hydrogen evolution reaction takes place at the cathode. An AEM cell usually consists of polar plates with serpentine channels in order to allow the flow of the reactants, Teflon gaskets to control the compression of the electrodes, and an ion exchange membrane that allows the conduction of the hydroxide ions, which is sandwiched between two electrodes consisting the catalyst layer. The combination of the membrane and the electrodes is called the membrane electrode assembly. The electrode usually consists of a porous transport layer, optionally a microporous layer, over which the catalyst layer is deposited. The catalyst layer consists of the catalyst support and the components of the active phase that are connected together using an alkaline exchange ionomer. In addition to acting as a binder, this ionomer provides pathways for the transport of hydroxide ions inside the catalyst layer and into the membrane. The state-of-art material for ammonia electrolysis in AEM conditions include stainless steel fiber paper as an anode PTL and carbon fiber paper as a cathode PTL, platinum iridium on carbon as an anode catalyst and the platinum on carbon as a cathode catalyst. As for the ionomer, naphthalene has been most commonly used, as well as polytetrafluoroethylene as a binder, with no study reported on the use of an alkaline exchange ionomer. Of course, changing the quantity and the nature of these material will impact the performance of the MEA. This performance that can be measured using the polarization curves, because the current density is in direct relation with the hydrogen production rate. This graph represents the only and the state-of-the-art polarization curves for ammonia electrolysis in AEM conditions. It has been obtained when using at the anode platinum iridium on carbon at a loading of 2.6 milligram per centimeter square, at the cathode platinum on carbon at a loading of 0.2 milligram per centimeter square, and an ion exchange membrane and PTFE as a binder. Since only 2 studies were reported in the literature on the recovery of hydrogen from ammonia in AEM electrolysis, the process needs to be optimized. The optimization can take the form of finding the best anode, the best electrode conditions, specifically in terms of catalyst loading and ionomer concentration. Since the ammonia oxidation reaction is the more sluggish and the less studied in the literature, the objectives of this part is to improve the anode conditions, specifically in terms of catalyst loadings and ionomer concentrations for the ammonia oxidation reactions. First, using commercial catalysts, and then in an attempt to improve the performance from the commercial catalyst, we prepare homemade ones. The evaluation of different materials start from the electrode fabrication, which consists of spraying a catalyst ink on a porous transport layer. The composition of this ink, which consists of the catalyst, the ionomer, and the dispersing medium, has a great impact on the final performance of the MEA. For this reason, we decide to prepare and evaluate different ink compositions, specifically working on the catalyst and the ionomer. After that, the MEA should be prepared by treating the membrane and assembling the cell. The polarization curves could then be obtained by testing this cell in real operating conditions in a designed hydrogen test bench. For this reason, and for this thesis, we specifically design a hydrogen test bench consisting of AEM electrolysis cell for the evaluation of different MEAs for the ammonia oxidation reaction. This test bench consists of an AEM single cell provided by dioxide materials and dedicated for water electrolysis applications. It has an active area of 6.25 centimeters square and provided with a commercial MEA containing nickel-based catalysts, an anion exchange membrane, Soutenance, and naphthalene as a binder. The test bench also consists of the reservoir, which contains the feed and the electrolyte solution, placed in a heating bath. The peristaltic pump allows the circulation of the feed into and out of the cell. PID controllers are used to control the temperature of the electrodes. The DC power supply provides the electrical current, and the data acquisition system is used for data storage. The obtained polarization curves were similar to that provided by the manufacturer, which allowed us to say that the performance of this test bench was validated. In order to recover hydrogen from ammonia using this test bench, it is necessary to adapt the material of the electrodes, specifically replacing them, the nickel-based catalysts by platinum-based ones. Due to time limitations, we will use commercially available cathodes, and the work will focus on the preparation of the anodes. This consists of obtaining a catalyst ink, which is a mixture of the desired catalyst to be used at the anode, the dispersing medium, which is a mixture of water and isopropanol, and the ionomer. In this case, it's chosen to be Soutenance in an attempt to improve the performance from the literature and for it to be compatible with the membrane. This ink is well sonicated and then sprayed on a stainless steel porous transport layer cut into the dimensions of the cell using a homemade spraying system in order to finally obtain the anode at the desired catalyst loading. After that, the MEA should be prepared, and we start with the activation of the membrane. The membrane chosen is a commercially available one, Soutenance, provided by dioxide materials. It has the following chemical formula, and it is received on the chloride form. These ions should be exchanged into hydroxide ones by immersing the membrane in 1 molar KOH for several hours. After that, the cell is assembled by mounting on top of each other the different components, starting with the anode gaskets, the prepared anode, the treated membrane, the cathode gasket, and the commercially available platinum on carbon cathode. The polar plates are then screwed together in order to obtain a cell ready for testing. Now for the results, we will start first by presenting those obtained with a commercial catalyst, where we will give evidence on the ammonia oxidation reaction, and then we will study the impact of several parameters, such as the impact of the cathode catalyst loading, the anode catalyst loading, the Soutenance concentration on the anode side, and the impact of the electrolyte concentration. In an attempt to improve the performance, we will prepare and evaluate different homemade catalysts towards the ammonia oxidation reaction. We'll start first with a commercial catalyst, which is chosen to be a platinum iridium supported on specific type of carbon black Vulcan XC72. The SEM images show a porous morphology with lots of micro and the macropores and a carbon particle size distribution peaking around 45 nanometers. These statistics were obtained by measuring 200 particles. This catalyst has a specific surface area of 210 meters square per gram and the pore volume of 0.46 centimeter cube per gram. The TEM analysis shows a very good dispersion of the nanoparticles, platinum and iridium, with a nanoparticle size distribution peaking around 2.4 nanometers. The EDX analysis shows the presence of platinum and iridium at a total metal loading of 17 weight%, consisting of 84 weight% of platinum, and the rest is iridium. First, we start by giving evidence on the ammonia oxidation reaction, and for this we perform two different runs in the presence and in the absence of ammonia. In the absence of ammonia, a voltage of 1.6 volt is required in order to obtain a current density of 10 milliampere per centimeter square. When ammonia is introduced into the system, this voltage decreases to 0.6 volt. It was also possible to calculate the electrical energy consumption as well as the energy efficiency of the system by taking into account the lower heating value of ammonia. By comparing our data to the literature, they were quite close. However, room for improvement was still available due to the differences in the operating conditions used. For this, we decide to study the impact of several parameters. We start first with the cathode loading, and we change this loading from 0.1 to 0.5 milligram per centimeter square. No effect on the performance of the MEA was obtained when inside this range. This means that at a loading of 0.1 milligram per centimeter square, we could have sufficient number of active sites in order to catalyze the hydrogen evolution reaction at the cathode, and it could be interesting in the future to try loadings lower than 0.1. As for the anode loading, it was changed from 0.9 to 2.7 milligram per centimeter square. The best conditions were obtained at a loading of 1.8 milligram per centimeter square, and the optimum could be ranging between 1.8 and 2.7, which is conforming to the data reported in the literature. The reason behind that could be the presence of sufficient number of active sites, but also the optimum thickness of the catalyst layer, which would result in the lowest mass transport limitations and the lowest electrical resistance. For the rest of the tests, we will choose an anode loading that lies inside this range, specifically 2 milligram per centimeter square. We also studied the impact of the ionomer concentration because it has a great impact on the performance of the MEA. For this, we increased this loading from 5 to 10 weight%. Improved performance was obtained at the lower ionomer concentration due to the lower mass transport limitations that could be present at a sustaion of 10 weight%. Because the literature used higher electrolyte concentration, we also changed this concentration from 1M to 5M KOH. Only slight improvements were observed. Only slight improvements were observed due to the higher ionic conductivity at the higher electrolyte concentrations. Since these improvements were not really significant, we chose to operate with 1 molar KOH for the rest of the tests. In order to test the durability of the catalysts, we conduct chronopotentiometry at 44 milliampere per centimeter square. We observe a slight increase in the voltage at the beginning of the reaction, which could be attributed to the non-replacement of ammonia molecules as they are being consumed. A sharp increase in the voltage is then observed, which stabilizes at 1.6 volt, which is already the region of water oxidation. In order to try to understand this phenomena, we propose several hypotheses. Either the complete consumption of ammonia after 1000 seconds, the complete deactivation of the platinum-iridium active sites after this time, strong mass transport limitations in the support cores, and a matter of catalyst turnover, which is the number of the number of mole of reactants that could be transformed into products by 1 mole of the catalyst. After calculating the mole percent of ammonia consumed during 1000 seconds to be 0.1 mole percent, it was possible for us to eliminate the first hypothesis. In order to understand more, we conduct different runs at successive time intervals chosen to be between 0 and 3 hours. A DT of 0 means that the 2 runs were conducted successively. And we compare our data to the initial run. This graph shows that after 3 hours, it was possible to recover 90% of the performance of the MEA. And by going back to our hypothesis, it was possible for us to eliminate the second one. This means that this leaves us with 2 possible explanations, which is the mass transport limitations for ammonia inside the catalyst support, which means that we should find a support having an optimum pore size, or it's a matter of catalyst turnover, which means that we should research more active catalysts. At the end of this study, with the commercial catalyst, we could say that there was no effect on the performance, on the effect of the cathode loading on the performance of the MEA between 0.1 and 0.5 milligram per centimeter square. The anode conditions that produced the best results include platinum iridium on carbon at a loading of 1.8 milligram per centimeter square and sustaining weight percent of 5 weight percent. Improved performance were obtained at the higher electrolyte concentration due to the improved ionic conductivity, and the water oxidation reaction is proceeding at the expense of the ammonia oxidation reaction, which means possibly we should either work on the catalyst support or the active phase. For the rest of the time, we chose to work on the active phase and we prepare our own homemade catalysts. All these results were communicated in the ECS conference that was held in Boston in May 2023. Now, for the commercial catalysts, we prepare single metallic platinum and iridium supported on carbon, as well as bimetallic platinum iridium on carbon. We use the polyol synthesis, which consists in reducing the metal salts into metal nanoparticles, using a strong reducing agent, ethylene glycol, and a temperature of 160 degrees C. Carbon black Vulcan XC72 was used, which is similar to that in a commercial catalyst. Hydrochloric acid was used in order to enhance the deposition of the nanoparticles on the carbon support. After that, the mixture was filtered, washed, and dried in order to obtain the supported nanoparticles. These catalysts were characterized first using the N2 sorption, where we obtained different similar adsorption isotherms for all the catalysts showing type 2 curves. Similar surface area was obtained for the single metals, with slightly lower one for the bimetallic catalyst. The same observation also was obtained with the pore volume. As for the BGH plot, it showed similar pore sizes for all the catalysts, peaking at around 1.5 nanometer. The SEM images show a porous morphology for all the catalysts and a carbon particle size distribution, peaking at around 44 nanometer for all catalysts. The EDX analysis shows the presence of platinum and iridium where needed. These values were really important in order to adjust the calculations of the anode catalyst loading. The TEM images show good dispersion of the nanoparticles with the particle size distribution ranging between 2 to 3 nanometer depending on the metal particle. This means that the polyol synthesis succeeded in preparing nanoparticles in the desired size range. Now we start by evaluating these catalysts, and we start with platinum on carbon. It was prepared with at an anode loading of 2 milligram per centimeter square and sustaining 5.8%. 3 different PTLs were prepared in order to check for the reproducibility of the results, which were quite reproducible, which means that the catalyst synthesis and the spraying process were well controlled. We also evaluate the impact of, we also evaluate the performance of the different prepared catalysts. Single iridium on carbon provided very poor performance toward the ammonia oxidation reaction with a peak current density of 16 milliampere per centimeter square at 0.95 volt. Platinum on carbon produced the highest current density with a peak of 67 milliampere per centimeter square at 0.9 volt. Platinum iridium was more advantageous in the low potential region. However, its peak current density lied between that of platinum and iridium. Although the role of adding iridium in platinum-iridium catalysts was controversial in the literature, where some concluded that platinum-iridium produced higher peak current densities than single platinum, our results were conforming to those who concluded that platinum-iridium provided an intermediate performance. By comparing our data to the literature, our platinum-iridium provided better performances. As for our platinum on carbon provided better performances. As for platinum iridium, the performance lied in the range between a commercial catalyst and that reported in the literature. As for the recovery time, it was calculated and evaluated for platinum and platinum iridium. For platinum iridium, 100% of the performance of the MEA could be recovered after 3 hours, while only 60% of this performance was recovered for platinum on carbon. Even after 19 hours, only 90% of the performance was recovered. From this graph, it's really difficult to conclude on the impact of the turnover on the recovery time, because we really don't know what's happening between 3 and 19 hours. This means that there could be not only a problem of turnover, but also a problem of mass transport limitations inside the catalyst pores. It is also interesting to see that the best achieved performance for platinum and carbon is not the same as the initial performance. This could be related to the fact that iridium could be oxidizing into an activated oxidation state as the electrolysis take place. This hypothesis, however, needs to be validated. At the end of this study, we could say that the polyol synthesis succeeded in preparing catalysts in the desired size range. The results for all the catalysts were reproducible, which means that the catalyst synthesis and the spraying process were well controlled. Platinum on carbon produced the highest current densities, while platinum iridium on carbon was more advantageous in the low potential region. And there's a slight difference in the recovery time between platinum and platinum iridium on carbon, which means that this could be a matter of turnover in addition to mass transport limitations. At the end of this presentation, some key takeaways are to be retained. Concerning the techno-economic assessment, in a current scenario parameter, the cheapest option to reconvert ammonia is using a membrane technology for large-scale applications. In a future case scenario, all the prices of hydrogen will decrease to less than $8 per kilogram, and using ammonia as a liquid hydrogen carrier could be cost competitive to liquid hydrogen transportation. This study could be further ameliorated, first by including in the techno-economic assessment AEM ammonia electrolysis rather than the conventional liquid alkaline electrolysis, as now we have sufficient kinetic data. We could study the impact of the carbon footprint on the system, and we could study the flexibility of using ammonia on the energy system. And in this case, it would be possible to use the same electrolyzer to electrolyze ammonia when the electricity prices are expensive, and to electrolyze water when the electricity prices are cheap. As for the second part, using a commercial catalyst, the best anode conditions were obtained with platinum iridium on carbon at a loading of 1.8 milligram per centimeter square and 5 weight% of sustaion. The catalysts were not really durable because the water oxidation reaction was taking place at the expense of the ammonia oxidation reaction. For the homemade catalyst, platinum on carbon produced the highest current density, while platinum iridium on carbon was more advantageous in the low potential region. And the slight difference in the recovery time between platinum and platinum iridium on carbon means that there could be a problem of catalyst turnover, but also mass transport limitations inside the pores of the catalyst. And it could be interesting to prepare a support that has an optimum pore size, specifically carbon aerogels, because it is possible to control their pore size distribution. It would also be interesting to understand the reason behind the difference in the recovery time in the future. At the end, I would like to thank everyone who helped in the progress of this, in the success of this PhD, specifically the technical assistants from the Materials and Processes Lab, the SEMEF for their characterization equipment, IMRA Europe for the TEM analysis, and Sambio for the funds. Thank you for your attention.
Okay, thank you, Riham, for this very clear presentation. We're going to move now into the second part of this examination, which is going to be the questions with the members of the jury and the discussion. And we're going to start with the two rapporteurs. First of all, with the questions and comments of Mr. Loïc Assou.
Thank you very much, Mrs. President. First of all, Riham, would you prefer me to ask you the questions in French or in English?
In English, please.
In English, okay, right. So thank you for the nice and clear presentation. And first of all, I would like to acknowledge your supervisors, so Christian and Pedro, for inviting me to read and be present here for your defense. It was a very interesting piece of work. So first of all, I would like to congratulate you for this work, which is quite complete with two main parts. Let's say the technico-economic assessment, which is by its own full study actually, and the second part with a very deep experimental work, including the development of the test bench that was not available at the beginning of your work, and then the implementation of different materials. So again, it's quite a complete piece of work in this second part. So like two topics in one, let's say. So it's so I would like to congratulate you for this work.
Thank you.
Your manuscript was well written. I mean, both in the formal aspect and also with the results. There is many results in your manuscript, with a lot of references. So with a deep, I mean, assessment of the literature on this topic, which is quite innovative actually. We know that hydrogen is a hot topic at the moment, and ammonia can open very interesting opportunities. So yeah, I have some comments and some questions on your work. So as you mentioned in your technico-economical assessments, so it can be interesting to use ammonia for hydrogen transportation, especially when comparing to liquid hydrogen. But first of all, actually, I will have a question regarding the feedstock of ammonia. So did you consider that ammonia is provided from a green way? Or
Yes.
in your study, is it like mixed? And
No,
how is produced ammonia actually?
It was produced in a green way, specifically from the production of hydrogen from water electrolyzers. But that's why it has a very high price.
Okay, Yeah, that's why. Yeah, because the price is quite high. Actually, yes. There is a table in which you compare the price of your study with different prices from
yes,
the literature. It's like the double, yeah, almost the double of the price that you
yes,
find
because
in the
they don't
literature.
consider green ammonia, renewable ammonia.
Okay, okay, okay. And so to make it economically interesting, actually, do you think we can envisage like a mixture of green and not green ammonia to lower the cost? Because still the cost of the produced hydrogen is much higher than conventional cost of hydrogen produced from conventional way of producing.
Yes,
hydrogen.
it is still, but we really expect huge decreases in the prices with the huge decrease that we expect in the electrolyzer capex in the future. So not in the long term, we would have maybe cheap ammonia, renewable ammonia.
Yeah, it's very important in the hypothesis to consider green ammonia because, as you mentioned in your conclusion, actually the footprint, the carbon footprint is very
low.
important.
Yes, but in my process, it's going to be very low because it will come only from the fabrication of the equipment. Because inside my process itself, even for the furnace and providing energy, I'm using ammonia. Okay, there is also the question of, if we consider electrolysis, the question of electricity and the footprint of electricity, which is yes, the electricity is coming from the grid, so there's a share of the renewables today, and maybe some nuclear, coal, and gas. There is carbon coming from the electricity. That's true. Okay, okay, okay. Yeah, it's very important to mention it actually, and. Okay, so yes, if we go to the electrolysis part, so when you make the sizing and you try to calculate the dimension and the number of cells of your electrolyzers to supply enough amount of hydrogen, so you found that it's like 1,120 cells. Is it's a big stack? Do you have some comment on it? Yes, it will depend on the active area of the electrodes. So for me, I chose a random number, but in the manuscript, there's a relation between the active area of the electrodes and the number of cells. So it's always a compromise. It's a very big stack because we are producing high power. We need high power. So how did you decide the size actually of your membrane? And it's I assumed the 25 centimeter cell with the 25 centimeter square as active area randomly. Okay, because if we compare with a conventional electrolyzer for water electrolysis, the size is much bigger actually than 25 square centimeter. And do you think we can increase or enlarge the size of your membrane, of your cells actually? Yes, we could increase the size of the active area. We need to have more catalysts, but it will be at the expense. We will have less cells. So at the end, it's a compromise. In other words, do you think it's better to have less cells with bigger dimensions? I think it's better if it's more compact. Lower dimensions. For me, I think it's better if it's more compact. So if we have less number of cells. Okay, yeah, I do agree with this. Yeah. Okay. Yeah, just a comment also. It's page yeah, regarding the renewable sources of energy. Yeah, you mentioned it's page 59 that the renewable energy will remain a rare resource. Actually, I do not completely agree with this because, for example, if you consider solar energy, I mean, we'll receive a lot of energy from sun. So it's not the energy resource itself actually that will be rare, but it's more the way of converting this resource of energy. Do you have some comment on that? It's a very general question actually. I just wanted to have your point of view. You agree with this? If we consider sunlight, for example,
within a few minutes, actually, we receive enough energy
Yes,
to meet the need of 1 year, actually.
Yes, the problem with the renewable energy actually all the time is the flexibility, because we need to store it because it's not really available all the time. Yes. So the main problem is the flexibility on the energy system. That is the problem that it will create.
Yeah, actually the intermittency and the fluctuation actually of this resource of energy, pushes us actually to develop highly efficient systems to convert this energy, and robust systems also to be able to combine them with this intermittency and variable source of energy. Okay. So maybe I will move now to the second part of your work. So the electrolysis part. First of all, maybe just a question. So you consider the three different ways with thermal decomposition and electrolysis. So why you decided actually in the second part of the thesis to specifically work on electrolysis and not on thermal decomposition?
Yes. First, because thermal decomposition technologies are more mature, and as I said in my presentation, there are already large-scale ammonia crackers that are being constructed today, which leaves little room for further optimization of the process. And also because we have experience in doing electrolysis in the lab, so we chose electrolysis.
Okay. So so in the second part, so it's a big piece of work actually with the development of the test bench, and then you completely test it, qualify it, and then test a commercial catalyst, and then you develop your own catalyst. So it's a very nice work. Maybe some comment. So first of all, I would like to go back on the let's say oxygen and hydrogen evolution reactions. So you tell us, it's page 71, that in alkaline medium, actually the two reactions suffer of slow kinetics. Can you explain us a little bit more why in alkaline medium, maybe as compared to acidic medium, the kinetics of the reactions are slower? What is behind this?
I think first there's the impact of the mobility of the hydroxide ions compared to the mobility of the protons, because in alkaline, because protons are more mobile, so it could impact the rate of the reaction. But also there's the fact that in alkaline medium, most of the time we are using nickel-based catalysts and not precious metals who have very close performance to precious metals, but slightly lower kinetics.
Okay. And I also had a questions regarding your choice in selecting the catalyst for the ammonia oxidation reaction. So finally, you selected only noble metal and platinum-based metals.
Yes.
Why? And do you think it will be interesting in future for industrial scale implementation?
Why?
For costs?
Yes. Why I chose platinum iridium? Because for the moment, actually in the literature, there have been some nickel-based catalysts that were tested, but the results were not very promising because these catalysts have a very high onset potential. So compared to platinum, where you have onset potential of 0.405 volt, in the presence of nickel-based catalysts, pure nickel catalysts, you have an onset potential of 1.4 or 1.5, which is already the same as water oxidation. So these catalysts were not really promising, and I chose platinum iridium because there are very few reported articles in the literature. And at the beginning, I just wanted to make sure that my test bench is operating in the right way. So just to validate my results to the commercial catalyst, to the catalyst reported in the literature. And could it be interesting in the future? I'm not really sure. Platinum and iridium together is very interesting for large scale applications. We already have so much problems. They are scarce and expensive. And they are now used everywhere. We want them in fuel cells and electrolyzers. We want them everywhere. So it's not going to be interesting. But it could be maybe interesting to couple nickel-based to platinum-based catalysts like PT&I. It has never been tested. I didn't test it, but it could be one of the perspective. We'll see.
Okay, interesting. Yeah, actually, as I have read in your manuscript, there is mainly, let's say, one publication, the one of Viscardi, with which you compare actually your results, and not too many others actually.
Yes. Specifically for the recovery of hydrogen in AM conditions, I didn't find so much articles.
Okay, so then, yeah, so in your results, I mean, there is always this competitive reactions, let's say, between the ammonia oxidation reaction and the oxygen evolution reaction, or the water oxidation reaction. So how you can accurately like separate the two reactions and to ascribe the onset potential at which each reaction starts.
So during my tests, for example, if we go to, I don't remember where. First, when I tried to give evidence on the ammonia oxidation reaction. So in this slide, specifically, we could see that this is in the absence of ammonia. So this is completely water electrolysis reaction. And this is in the presence of ammonia. And you can see that theoretically the water oxidation reaction starts at around here, but practically it starts here. So throughout the whole range of the test, when I have ammonia, I'm only producing hydrogen from ammonia electrolysis. So also for the rest of the tests, I tried to, when I operate that cell, I tried to limit the maximum voltage to 1 volt. So I neglect the impact of the water oxidation reaction and study only the production of hydrogen from ammonia.
Okay. In terms, so you quite so roughly characterize the physico-chemical properties of your materials with TEM, BET, and chemical analysis as well. But also the structure of the material is important, and you mentioned it in the literature part of your report. For example, specific orientation of platinum can very much improve actually the performance of the reaction. So did you look at the crystal structure and the orientation of your materials? And do you think this is also something that could have been checked to?
Yes, I think it's very important to check it, because from the literature we could see that it has really great influence. If you don't have the right plane for platinum, crystal plane, it will be complicated to have a good AOR performance. I didn't look into it because we didn't have the time to do that, but I think it could be really interesting to see it and to check if we don't really have the right plane, how could we have it, and to improve the performance.
But from the protocol of synthesis you used, you expect to have this specific orientation, or you're not sure at all?
I'm not sure, actually. I don't know. I didn't look into that.
Okay. And you mentioned also some effect of leaching actually of the catalyst.
Yes. Yes.
So yeah, of course, this will have a strong influence of the performance.
Leaching of the catalyst mainly is related actually because we prepare different ink compositions, each having different ionomer concentration. So if the ionomer concentration is not really enough, we could expect leaching of the catalyst from the porous transport layer. Like the catalyst is being removed from this layer and it goes into the electrolyte solution. Of course, it will have an impact of the performance, but it's not really related to the degradation of the catalyst itself. It's more related, the thing that I described in my manuscript, to the low amount of ionomer concentration in the catalyst layer.
Okay. Yeah, so there is an optimum. I mean, in terms of performance, you need to optimize the concentration of ionomer. But if it's too less, yeah, you can have some leaching effect.
Exactly.
So yeah, it's like a compromise to find to get appropriate performance. Okay.
Yes.
Okay. I have also questions actually about the catalyst themselves also. So you did chemical characterization. Are you sure it's metallic metallic catalyst, or it can be like a mixture of oxides and metals, or?
I didn't look into that. It could be, there could be some oxides. I didn't really characterize to know, but it's very possible.
Okay. Okay.
I think so.
Okay. And you mentioned also the impact of the number of catalytic sites actually that are accessible for the reactions. So it's one of your hypotheses actually that could influence the performance of the systems. So you did not characterize this part, or you did not validate this hypothesis.
Yes.
But even though, do you have some idea of some techniques, experimental techniques that you could use to characterize this aspect?
I don't think I do.
Yeah, it's because actually it's always this problem, you know, at a microscopic scale, you have the response of your electrochemical system. But then if you look at the very local scale and at the catalytic site scale, you can very much understand actually the mechanisms and optimize them to have then a better electrochemical response at the macro scale, let's say.
Yes.
Okay. Okay, I don't know about the time. Maybe, just one or two last question. Also, I was wondering, did you analyze the liquid phase of in your reactor? I mean, is there only hydrogen that you produce, or because I think you mentioned also maybe that you could have like nitrate and nitrite actually, depending on the potential.
Yes, I didn't analyze. I'm not sure. Yes, we could have some nitrites.
Okay. And do you think it can like poison also the catalyst and have some influence on the performance?
It, according to the literature, it poisons the catalyst actually. So it could be, but I don't know. I don't know how much we are producing of the nitrates, nitrites. Is it really quantity enough to poison? I don't know.
Okay. And again, do you have any idea of experimental setup that you could use to
characterize
this?
Yeah. Yeah, I don't.
Okay, no problem. So I have other questions, but I think I will stop here. So congratulations again for this nice piece of work, for the very clear and pedagogical presentation. Also the durability. I didn't ask you too many questions about this, but it was good. You went deeper in the presentation than what you did in the manuscript. So it was also very good. And durability is a very big question also. And you tested your catalyst for like 3 hours, I think, maximum.
More like 1 hour.
Yeah. So longer tests are of course required to validate
but we already
the robustness and
already at 1 hour the catalysts are not durable, so that's why we stopped.
Yes, sure. Okay, so thank you, and I wish you all the best for future.
Thank you.
Merci, merci Loïc. Donc, I'm now going to hand over to the other reporter, who is a Professor Ange Nziou.
Thank you, Mrs. President. And first of all, I would like to thank Christian, for inviting me to join this jury. And sorry again for the delay in sending the report. And I really enjoyed listening to Rian and reading the manuscript as well as listening to the presentation that found very clear, very comprehensive, and covering most of the aspects that were developed in the manuscript, and also the temptation of responding to the question that were raised in the report. And this is much appreciated too. And some of the questions have been already been asked and then addressed. So I'm going to move on to three main, let's say, topics with you. First one's going to be the reactions, and the second one, the core of the study. We could see that it's the catalyst. So I'm going to spend some time with you discussing about the catalyst. And the third is on the environmental assessment aspect, as far as the CO2, the carbon balance is concerned, for example. So let's start with the slide 5, please. If you could have it displayed, we were talking about the other comparison with other technologies. Okay, okay. Here you did mention the TRL for the electrolysis, and saying this is the most mature, let's say, technology. And which are the others? Have you ever, the hydrogen, as the response to the question of the first rapporteur, you were saying that the hydrogen is renewable and it comes from electrolysis. Did you ever seen the other source of, let's say, green hydrogen and the thermal decomposition of, let's say, various materials to get sustainable hydrogen? Did you make this comparison? For example, the biomass gasification, to be much more specific. Have you ever made this comparison and see what's going on in that field?
You mean other sources for hydrogen production?
Yes.
I didn't look into that because I mean, my purpose was to produce hydrogen from ammonia, and I only looked into the processes to produce hydrogen from ammonia. No, I didn't look into the gasification of biomass.
Okay, it's just a matter of curiosity. So why I'm heading towards this, and the second aspect that I wanted to cover is the reaction. And I haven't seen, for example, in what you've been presenting, so in a manuscript, the thermal effect, for example, and the enthalpy of reaction. We do have a catalyst. You were mentioning in many of your, let's say, discussion that the heat and mass transferred are important for the conversion, right? And if, for example, what's the enthalpy of the reaction of storing hydrogen with ammonia? Is it exo, endo?
So it's basically this reaction.
Okay, you see, there's a significant release of energy, right? You could see the enthalpy in R1. And did you ever think on how this changing, because the enthalpy will generate a change in temperature in the system. And if you look at the Arrhenius law, it's going to have an impact on your reaction. Did you ever investigate, let's say, the thermodynamic aspect? What's going to be the impact of the heat released on the conversion rate, on the mass transfer, on the catalyst deactivation, on the phase distribution. This is an important piece of the work. I just want to hear your point on this. Could you try? What's your point? What will it be if the enthalpy is m delta T, right? Which means you're going to have a change in temperature in the system, and your reaction is thermal driven, which means it's going to have an impact on reaction rate. It's going to have an impact on the conversion, and most likely on mass and heat transfer, and on everything else that you have described. What do you think could have been done, or what could have been the impact, if you guess based on what you've done?
You mean the impact on the...
I mean the whole chain, the conversion and the catalyst and the change in temperature in the system because of the exothermicity of the reaction, which consume, as you have seen, 4.3 kilowatt per kilogram of hydrogen.
Sorry? Can you answer the question? Yeah, I don't have an answer.
You don't. It's fine. You just tell me. You cannot have the answer on everything, right? You've done a lot of work already, so you can just say, okay, good. Let's say, let me take in a different way. And you've done mostly kinetics and mass transfers. And there's the discussion with the previous speaker, where, for example, on the competition between the ammonia reduction and water reduction. And with equilibrium thermodynamic prediction, you could have, let's say, made your mind on which one controls the process, for example. This could be, for example, for future works. And since you've been operating at quite high temperature and high pressure as well, and let's say adding on this kinetic and transfer studies, some, let's say, thermodynamic piece will enable most likely a better understanding of the phenomena and the competition. Okay, it's fine. Let's move on. Let me come to the catalyst then. And you were having this discussion with a previous speaker. You've used the literature, the commercial catalyst, and you've tried some of them. For example, if I take on slide 11, please. Okay, slide 11. Here we have, yes, this one, for instance. We have this condition, pressure, temperature, and ruthenium. And did you evaluate the time on screen? And yes, how long it takes for the catalyst to, on the PSA, to deactivate? And for example, does it impact the conversion? Did you spend some time on seeing the behavior of the catalyst after the measure of the porosity, for example?
I did not.
It's okay, but what do you think could have been done? In other words, do you consider that what you've done is optimum condition, or it could have been improved? And what's your views? Based on what you've done, you can give me just your feeling, based on the data that you've been able to collect.
You mean that the catalyst could have been another one, an optimum one?
No. Usually when you use a catalyst, there's as the reaction goes along, there's a deactivation that comes for whatever reason, and it could be a co-affection where when you have some carbon somewhere, you don't have carbon here, and it could be the pore clogging, and because of let's say a neoformed component that may clog the port, or it could be just the chemical change.
Yes, I consider the effect of catalyst deactivation in my process because I consider the catalyst lifetime of 5 years. So for me, every 5 years, the catalyst is being replaced.
And how did you come to the 5 years?
It was an assumption.
And what was the assumption based on?
Generally, how long it takes for catalysts to degrade in thermal decomposition, but not specifically for the ammonia thermal decomposition.
That's why I'm asking, because it could be very variable, depend on the processes.
Yes. It will depend, yes, I agree, but I didn't have data, so I just took an assumption.
Okay. Good. But have you seen anything else in the literature, for instance, in other catalysts with the time that they estimate?
I didn't really look into it so much.
Oh, okay, good. So then I come to the discussion that you had already with my colleague, previous speaker. And here the reasoning is mostly based on, let's say, stressing the sustainability of the approach that started with producing hydrogen from renewable source and storing it in a certain way, and then have it transport with all the advantages that you've been mentioning. And if we look at this, at the end of the day, what is the key in the process is the catalyst. And here you've been using, and in this example that we have here, and later on, mostly ruthenium, iridium, and platinum. And the question I asked you in my report was why you didn't try to green the catalyst as well, at least on the homemade ones, trying to get yourself far from strategic and rare metals and to try others, because you may have seen, of course, there's this nickel, cobalt, and iron. There are a couple of options. Why you didn't try to green also to increase the sustainability of your process and using, let's say, much more conventional metal catalyst?
Yes, it would have been possible to do that. But what I tried to do when I prepared the homemade catalysts was to study the effect of turnover. And I wanted also to see if I was preparing catalysts that have really better performance from the commercial one. But in the next step, it could be first to establish the catalyst synthesis process, and then it could be good to try to synthesize other less strategic metals, such as nickel and cobalt. But here I was really at the beginning of the study. In the future, it could be a good perspective.
Okay, thank you. So from in some of the slides, you were showing the characteristics such as particle size distribution and the porosity. If I ask you overall, you do have a couple of parameters to play with, and the pressure and the temperature and the catalyst characteristics, which means the chemical composition and the physical characteristics. if I ask you to give an hierarchy to make your process effective, efficient, what will be, let's say, the hierarchy in the affecting parameters?
Which process?
For you, for storing hydrogen.
Electrolysis?
Yeah, electrolysis, and what will be the most important parameters? Is it the composition, the chemical composition of the catalyst? Is it the physical characteristics? Is it the temperature and pressure? What's the, if you give, because you didn't give an opinion at the end, you investigate the impact of all of them, but you didn't tell us that if I have to make a choices, I will rather focus on this one and against this one. What would be your like hierarchy? What's the most important to as a take-home message on the parameter?
There are lots of parameters that influence the process, but I think that the composition of the catalyst is the most important one. Because when I presented my results with different catalysts, we could see that if we don't have, for example, platinum in the catalyst, we only have iridium, we have very, very poor performance.
Yeah.
So we cannot expect performance without platinum. Concerning the other effects, the effect of pressure, I didn't really study it. I have no idea. But the temperature also plays an important role, and it could be the next parameter in the process. We also have the effect of the electrolyzer components, specifically the membrane, which should have a high ionic conductivity. Otherwise, the performance will be really poor. I think these are the three main parameters for me.
Okay, good. So let me move on to another, let's say, bench of issues. The CO2, as I told you in my report, I was surprised to see such a great study, because you did a great job, without a mention to CO2. Now, in a perspective, you did mention the carbon footprint. And if I look at the whole value chain, and it was mentioned before already, from the hydrogen production, electrolysis, you're going to use energy source anyway. It could be nuclear or something else to get the electricity. And here on the slide that we have in front of us, you're going to generate this enthalpy and energy, what to do with the energy, for example, and with the catalyst production as well. And you did use a certain temperature, certain chemicals to get to produce your homemade catalyst, and the commercial catalyst has also some carbon footprint. This could have been interesting to go to the end of the demonstration of the sustainability of the approach and to see the carbon footprint in terms, at least CO2 of the step that you have used. Saying so, I know that you've done a lot already, but I still want to hear from you on if you have to make like a carbon balance of the process that you've developed, what will be, let's say, the items or materials that you leverage on?
Can you repeat the question, please?
And if I have to make a CO2 balance of the process, of the value chain that you have developed, where do you believe I could be successful in saying this has a low impact, or where could it be burdening, or where could it be problematic? Even if everything looks green, right? But you see if the way you make the catalyst, the electricity that you use, and the recyclability of rare metals? And where do you believe the most carbon impact could come in this value chain?
I think it's from the electricity, maybe, because for the moment we don't have high shares of the renewables.
Because the question is about in the chemistry that we use in making the catalyst, there's also a carbon footprint. So what is your comment on that carbon footprint?
I hear someone talking. I don't know if it's only me.
Yes. Yes, the catalysts are not really green. And me, I was using already commercial supports of carbon that I'm pretty sure that they have. I don't know how they are produced actually, not really sure. But they could have a carbon impact. Also, the production of the rare metals could have also carbon impact. That's true. So what could have been done? I'm not really sure how to decrease the carbon impact, but yes, it could be worth studying.
Okay. So I don't want to abuse on the time. First of all, thank you for trying your best in responding. And I would like to congratulate you again for the lot of work that you've done. And for someone knowing a little bit the field, I consider this to be a significant contribution to the body of knowledge. And I would like to congratulate for that, and I wish you all the best for the next steps. Go give words back to the president.
Thank you very much for all of these questions and for the discussion. And I'm going to hand over now to Professor Gaël Maranzana.
Thank you, Mrs. President. First of all, I would like to thank Christian for the invitation. I appreciated very much to review this work. I learned a lot, and especially now I can put numbers on the costs of the different steps to transport the energy from where it is cheap to where it is used. So your subject is about the recovery of hydrogen from ammonia. So you assumed several things about the cost of ammonia. 1,000 euros for now for renewable ammonia, and 500 euros per ton in the future. And in the best of your cases, you found a levelized cost of hydrogen of 4.2 euros per kilogram in Europe. This is the best cost you calculated. And 4.2 euros per kilogram of hydrogen, this means 130 euros per megawatt hour of energy. So this means a cost of hydrogen that is almost the cost of the new nuclear in France. So this means that at the end, there is no interest in doing electricity with this hydrogen, because the electricity would be too expensive. Okay. So, but this is a conclusion that is not shared by some people, especially in Germany. In Germany, there are many people that think that the model of the future will be to produce electricity from photovoltaics in North Africa at 10 euros per megawatt hour, and that we can transport this energy in the form of hydrogen or ammonia in Europe and use this hydrogen or ammonia to produce again electricity. What is your feeling about this model?
The thing is that the hydrogen I'm recovering from ammonia is not 100% dedicated for the production of electricity. Mainly, it's for decarbonizing the energy sector through by using it in the industries where it is necessary to use hydrogen to decarbonate, for example, the steel industry, or in the chemical industry where you need, for example, for refining of oil, you specifically need hydrogen and you don't really need electricity. So here in this case, our hydrogen could be interesting. Maybe it would not compete with the producing electricity because it will be so expensive, but and then there are cases where you really need hydrogen and you cannot replace it with electricity.
So for you, the German model is not really realistic?
I mean, yeah.
Okay, so of course, we have calculated the price of hydrogen, and we can discuss about this. I have another question about the storage, because you know that to store hydrogen, it's very expensive, and maybe you know also that it is mandatory to store energy. For example, in France, we have 90 days of oil consumption that is stored. This is mandatory because otherwise the market would be not stable at all. So we store 90 days of consumption of oil in France. So we will have also after the petrol, after the oil, we will have to store some energy in the form of hydrogen or ammonia. So I was wondering if you have, if you know the cost of ammonia storage. When compared with the cost of hydrogen storage.
I mean, it's I don't have a number in my head, but it's definitely much less expensive because the ammonia can be stored at very much milder conditions already. So you know, for the storage of liquid hydrogen, we need very thick and isolated storage tanks in order to minimize as much as possible the boil off. You have lots of losses, we need to avoid them. So it's less expensive, but I don't have a number I had to share now.
Okay, and because there is also another interest of what you have done is the interest is to do the interseasonal storage of your renewable energy that is produced in Europe, because we know how to store the energy between the night and the day, but not with an interseasonal time. Maybe it would be interesting to see if it is if the cost is good or not. Okay, so now for the second part of your work, page 71, you wrote that the kinetics for oxygen evolution reaction is worst in alkaline media when compared with acidic media. Can you confirm that?
Sorry, can you repeat the question?
I think you wrote that the kinetics of oxygen evolution reaction is worse in alkaline media when compared.
Is worse?
Yes.
Yes. I just explained to your colleague. I think that it is lower. It has lower kinetics in alkaline media because of two issues. The first is related to the lower mobility of the hydroxide ions as compared to the protons, which makes the reaction slower. And the second is related to the fact that in alkaline media, we tend to use nickel-based electrodes that are, while the benchmark catalysts remain to be precious ones, specifically iridium oxide, and it's also used in acidic media because we cannot really use nickel-based ones in the acidic. So these two issues, they impact the kinetics of the reaction.
I am not an electrochemist, but I was thinking that oxygen evolution reaction is faster in alkaline media than when compared with acidic media.
According to the literature, It's lower.
Okay. I don't know, maybe we have an electrochemist in the jury, but I think this is a...
But why would you think it's faster?
It is just measurements.
Okay.
And maybe this is why we can use other materials than iridium in alkaline media. But we will see. I have also a remark about the state of the art you have made in your introduction. Maybe you are a little optimistic about the performances of AEM water electrolysis. You wrote 1 amps per square centimeter at 1.8 volt with pure water.
At temperature of 85.
Yes, but with pure water, okay, it's possible, I think, to reach 1 amps per square centimeter at 1.8 volts with pure water. But in this condition, the durability is few hours. So it's not really realistic.
Okay.
We don't know. It is very difficult to use pure water because there are other degradation mechanisms that limits the lifetime.
Yes, I agree.
I think the main concern with your electrolysis system is the stability of the catalyst, because we know that platinum and carbon is not stable in alkaline media. Maybe you have not found some papers about that. The LEPME did some study about this. Do you know the mechanism of the particle detachment? No?
Not at all.
Not at all. I think the platinum catalyzed the formation of carbonates at the interface between the platinum particle and the carbon support. And these carbonates have detached the particles. At the end, even if the potential is very low, you have a detachment of the platinum particles from the carbon support. So
yes,
in my mind, this is not a catalyst that is stable in alkaline media. Even if the potential is low, after that, if the potential is high, you will have a lot of carbon corrosion. We can't use carbon as a support to do electrolysis, to do water electrolysis. Maybe for ammonia electrolysis, the potential is not so high.
Yes.
But do you know the potential of equilibrium for carbon corrosion?
I don't.
This is something like 0.2 in acidic media. In alkaline media, I don't know, but it is lower. So the carbon is not thermodynamically stable. And I don't think it's possible to get something that is stable with a carbon support. I don't want to ask too many questions, but just a last one. It's about the characterization of your electrode, because you, as you said, when you spray your ink on the PTL, the ink can come inside the PTL, and you lose some catalyst. And at the end, you don't know exactly what is the mass, what is the loading of your electrode.
Yeah, I know. I can measure it.
By how you can measure it?
Before and after spraying.
You write?
Yeah.
Yes, but if the catalyst is inside the PTL, it is not active.
I'm not sure. Why not?
Because if the catalyst is too far from the membrane, if the length between the membrane and the catalyst is more than 10 or 20 micrometers, the transfer of the OH minus won't be good. So at the end, you lose the catalyst when it is inside the PTL. And I was wondering if you have tried to do measurement like ECSA measurement to know the electrocatalytic surface area, the right one you have.
Yeah, I didn't do. I should have done maybe. I didn't do. Yes.
Okay.
But me, I would specifically like to emphasize on the fact that when I had problems during the spraying, when I was losing, it is because I didn't have an optimum spraying system. And after that, we worked on the spraying system and we could manage to not lose the PTL, the solution through the PTL. But I cannot really tell if there's a small quantity that's really going inside the pores. This I cannot really tell 100% that I don't have. But we really worked so much on the spraying system to improve the spraying at the end.
Okay. Thank you very much for your answer.
Thank you.
I have to congratulate you because you have done a lot of work, from the materials to the characterization at the cell level, and moreover there is also a technico-economic analysis. So you have done a very large amount of work.
Thank you.
And congratulations.
Merci beaucoup, Ariel. Je vais passer la parole maintenant à Mr. Julien Durst.
Thank you, Ms. President. First, thank you, Christian and Pedro, for the kind invitation to follow this work. And thank you, Riham, for the nice presentation. Very clear, super easy to follow, such as the manuscript that you wrote. It was really enjoyable to read on all parts. The first part I was not really a specialist on, so I learned a lot, and so I will keep all my questions for the second part, which I like the most, when it talks about materials and electrochemistry. And I will try to go a bit, touch a bit different topics, such as the experimental part, the way data have been measured and repeated about materials and fundamental kinetics. So first question regarding the setup that you are using, the cell, the electrolysis cell that you have. It's a 5 centimeter square or 6 centimeter square cell.
6.25.
Yes, and so I'm not, I don't have a lot of knowledge on such type of electrolysis cell, but in fuel cells, when we use small active area cells, 5 centimeters square or even below, it is to perform very specific measurements under what we call differential flow, meaning that we try to get rid of all mass transport limitation by operating at very high stoichiometries. And is it something equivalent that we have here? So we limit ourselves to a very small cell geometry in order to really look only at kinetics?
For me, I used the very small cell because I intended to prepare my own materials, my own MEAs, so I had to prepare catalysts to spray them. And if I have a 25 centimeter square cell, I would need to prepare a huge amount of materials. So for research purposes, I went to small cells.
Okay, for sure. Okay, but then it doesn't. So the results that you get on a small scale, 5 centimeter square, then it will be also applicable to larger cell, do you think? Or will there be additional losses to be considered?
I'm not really sure, actually.
And do you know, so is this a standard design that you have bought?
Yes.
Okay.
Yes.
And that other people in the field of electrolysis use?
I think they use more like 5 centimeters square. 6.25 is quite specific, but this was developed by Dioxide Materials, but I don't really know the reason why 6.25.
It was made by Dioxide.
It was made by them.
Okay. Good. Then a question on data, the precision on some data. Sometimes you go very precise in the number that you give in the manuscript. So for example, we can find that by page 114, when you give a peak particle size, you go down to the 2 digits after so even below the angstrom. So is this really
no, this is not really precise.
Okay.
The results were not really precise. It's very difficult to go to 0.001 nanometer to measure it.
Okay.
I think yes, it would only be enough to put one figure after the decimal.
Okay, so you think we can go at plus or minus 0.1
yes, maximum
angstrom, nanometer, sorry, for that measurement.
I think so.
Okay. Okay. Then another question regarding measurement accuracy when it comes to the measuring the ratio, the metal to carbon ratio, which is very important on a catalyst when later on you want to assume you have a certain metal loading in your electrodes. So at first you are doing an EDX analysis on a commercial platinum on carbon, 48% by mass. I think the results are page 115, and I think you end up with the exact weight ratio that is given. So the 48% as your catalyst, you end up you find 50% of carbon, 35% of platinum. So it fits well with what is given. Does it fit well with also what is given in the certificate of analysis of that catalyst? Is it a commercial catalyst?
It is a commercial catalyst, yes, and it was fitting well with what was provided.
Okay, and you find also traces of aluminum there.
It's not it's aluminum actually is used to improve the conductivity of the sample. So we normally spray, we put a layer of aluminum on all the samples before testing with the EDX analysis. So it's
okay. And then you use also EDX to determine the ratio of your homemade catalyst, the platinum and iridium. Do you know also other techniques or other ways that could have give you this the metal to carbon ratio? Since sometimes EDX is not maybe the
it's not
best
very precise.
quantitative. Would you have an idea of another method which would be more quantitative?
We wanted to do another technique, but we didn't have the time to do it. It's called X-ray fluorescence.
Okay.
To detect the exact quantities of platinum and iridium in the sample.
Okay. But this is a very important parameter also for us, and when we buy catalyst powder, we want to make sure that we have the right ratio. Typically, we go for thermal gravimetric analysis.
Yes.
This helps when you know area steps where you burn only the carbon and the residue is only metals.
That's true. I know it.
Again, about data, precision, repeatability. Have you tried to repeat multiple times the same test to see if it really gives the same results? I mean, here in terms of the electrochemistry, and would you say that the way that you were making the electrodes and assembling the cell and testing it, did it give very repeatable results?
Yes, actually, I also tried to prepare different catalysts all the time. I was also measuring their the loading of the metals. It was quite reproducible. For the spraying of the electrodes at the beginning, as I said, I had problems using the spraying process because it wasn't, I mean, it's the first time we do this thing in the lab. So we had to optimize the process at the beginning. I didn't have really reproducible results, but when I solved this problem, the results at the end with the homemade catalysts appear to be really quite reproducible.
Okay.
For all the catalysts.
Quite reproducible.
Quite reproducible.
What is quite?
Reproducible.
So
for example, if you look here at the for example, this was for platinum and carbon. I faced the same type of graphs when I did platinum iridium or iridium on carbon. So quite reproducible.
Okay. Then on the, I think we can, on on the polarization curves that you have shown, not in your presentation, but sometimes in your manuscripts, in the way that you show the current, you show a current in unit of amps per centimeter square per milligram, and which is a bit uncommon, or I'm not really. I haven't seen.
Yes, I agree. It's not really common. Usually, it's either in ampere per centimeter square or in ampere per gram of the catalyst. But because I said when I produced these kind of graphs, I really had a problem in the spraying, and so I was doing several tests. I was solving the problem of the spraying as I am doing the tests. So most of the time I didn't have really the same catalyst loading, and I wanted to normalize the results to the catalyst loading. So I had to divide ampere per centimeter square by the amount of the catalyst to normalize.
Okay. Because typically, or the way I've seen kinetic data presented, it's directly the amps per milligram.
I agree.
Or amps per centimeter square, but of the real active surface area of the material. So it's true that what you get from your setup is amps per geometric centimeter square, which can then be divided by the loading in milligram per centimeter square, which gives amps per milligram, or divided by the roughness factor to really have the amps per centimeter square of active surface area. So here it was just a bit not really common to see that kind of unit. And so, if we then really want to focus on the kinetic data, so here every time you are showing the raw data, or let's say the uncorrected data in terms of the potential as a function of the current. In order to really look into the kinetics, would you have or have you measured any EIS to extract the high frequency resistance of your device in order to correct from all the IR losses?
I'm sorry, I didn't understand. Did I measure what?
The high frequency resistance using electrochemical impedance spectroscopy in order to correct from the ohmic losses that you could have.
I didn't really.
Okay.
I didn't really measure that.
Did you have the equipments to do it?
I think we have them, yes, but I didn't have the time.
Okay. Did you try? Okay.
I didn't even try.
Okay. Okay. Because it could be quite helpful. Huh?
Yes,
because,
I think so. Yeah, that's true.
It can give you a lot of information about, of course, the OH conductivity of your membrane, but also how all your material are compressed into the cell. And so since it's this also helps to see every time that you are doing another measurement that okay, you are correctly in the right conditions, that allows you to compare all the results. And so that's one type of correction that one can do to a polarization curve. The other correction is since we are really looking at small currents in terms of milliamps per centimeter square, how does the gas crossover plays a role here? How does for example, the hydrogen that you would generate on the cathode side of your electrolysis cell would permeate and be oxidized on the anode side and would give a parasitic current?
I mean, I don't know. I didn't study the issue of crossover, so I'm not sure how much is the cross of the gases through the membrane.
Do you have a rough order of magnitude of the typical hydrogen crossover current on these materials?
I don't have a value in my head.
Okay. Me neither. Huh? on these specific membranes, but typically for membranes for fuel cells, which are 10, 15, 20 microns thick, the range is in the order of 5 to 10 milliamps per centimeter square. So we are in the range of the currents of that you're measuring something.
Okay.
The lower. And yeah, AEM, so anion exchange membranes are fascinating materials, also very difficult to handle. I worked at the time, like 10 years ago, with a Tokuyama membrane.
Yes.
And it was super complicated to have it not polluted by the CO2, even environmental CO2. Like, yes, they would deliver it. Yes,
that's true. There's this problem with AEMs.
Yeah, exactly.
Yes.
So the supplier would deliver it in chloride form. You would make all the effort to exchange it into OH.
Yes.
But then when you remove it, and
it will be polluted.
Exactly.
Yes, I agree.
And how does it work in your case? So are you working with membranes which are initially in a carbonated form?
No, they are in the chloride form, and I have to activate them.
Okay.
But I don't study the impact of the pollution.
Okay. So you activated the ex situ before the cell assembly?
Yes.
Okay. Then you transfer it?
I store it after activation.
You store
I store it in plastic bags inside the...
Which has air and 400 ppm
air
of CO2.
And, that's true. So there could be a CO2 pollution, but I didn't really study it, and I consider it's the same in all my tests. So I don't really study its impact.
Okay. Do you think there? So in fuel cell, when I was using this material for fuel cell application, you would really see a difference between the first and the cycle of your polarization curve that you record, where in the first cycle you would see the membrane which would still be in the carbonated form, and there were ways to remove the carbonate, or to convert the membrane from the carbonated to the OH form. And so here in your case, when you were looking at the very first cycle that you recorded, do you also see such very different change of the behavior of the material, which would indicate also that a change of the state of the membrane?
With the, like, if I run several tests with the same membrane?
Yeah, and especially on the very first cycle, on the really between the first, second, third cycle.
I don't really see a big change in the performance.
Okay. So I think I'm done for my question. So thank you very much. It's not an easy topic. It's not easy materials to handle. It's really not at all to make good science. But you really made a lot of effort to investigate, to look at very different parameters to convince us that what you are seeing is something which is true. So thank you for all this effort, and thank you for your work.
Thank you.
Okay, excuse me. So I just have a few comments on the manuscript, and then a couple of questions before I hand over to your supervisors. So on the manuscript, I certainly agree with everything that's been said up until now on the clarity of the script. I would just a couple of comments, and those that take care on when you reread and make the corrections in the final version. Check some of the abbreviations that you're using. Sometimes you're using AEM actually for meaning AEM water electrolysis. So just check for consistency in the abbreviations that you're using. Sometimes you use AE for alkaline electrolysis. Sometimes it's AWE, just for consistency. You use DAFC, I think, for direct ammonia fuel cell, whereas normally it's understood as being a direct alcohol fuel cell. So I don't think it's already a confusing enough area without introducing more confusion. So I think just be very careful not to use abbreviations that are already used for something else. One other comment is on your use of conductivity when you're referring to a membrane. Okay. Conductivity is an intrinsic property of the ionomer. And so strictly speaking, I know that lots of people have used this, make the same mistake because it is a mistake. Conductivity is of the ionomer, and we should talk about resistance when we're talking about the membrane. Okay. So one way of improving the performance of a fuel cell and electrolyzer is to use a thinner membrane, because you have an ionomer of the same conductivity but lower resistance. Okay. So as long as you understand that, perhaps you need to put an explanation and then say that, you know, for consistency with other texts or whatever, but a membrane has a resistance, it doesn't have a conductivity. Okay, so two points which are both kind of related to well, degradation or deactivation or whatever you want to call it. But first of all, I mean, you know, one thing that could be a showstopper is actually the deactivation that you see at the end of one run, as you call it. So you went through the different interpretations of why there is a loss of essentially a loss of performance and no further activation for the ammonia oxidation reaction. Did you think about, for example, putting a gas chromatograph at the anode side to actually see what you were producing? Because when you continue your reaction, then it evolves, as it were, over time into water splitting reaction. So that means that over the course of time, you might expect to see nitrogen evolution changing to oxygen evolution at your anode.
Yes.
I mean, you could actually analyze that by putting a GC at the anode outlet.
To check if I'm having oxygen, you mean?
Just to determine actually what you're producing in the reaction, because you're trying to interpret on the basis of polarization curves only.
Yes.
And that's actually insufficient.
Yes. It could have been a good idea. Maybe there is also production of some intermediates that take a little bit more time to dissolve. So yeah, we maybe could identify them.
Exactly. Exactly. So that would be, you know, in future work, something to think about. When I was looking at the literature as well, and the work not on AEM water electrolysis, but on ammonia oxidation, and in particular the work of Geraldine Botte, and she in her papers describes the use of electrochemical cleaning, as it were, of the catalyst surface, because if you switch to a different potential, then you can desorb species that are adsorbed. Did you think about doing that in your work?
I didn't think about it when I'm doing my work, but it could be one of the ideas, because if we have intermediates, we really need to desorb them, and maybe it could be one of the problems, like just to desorb them quickly with a certain technique, and then we will activate the catalyst again. I agree, but I didn't look into it.
So when you talk about the time taken needed to regenerate or recover, under what conditions did you actually keep your cell?
The same conditions of the test, but the cell is normally shut down. So if I have 1 molar KOH, I still have 1 molar KOH, the same as the test, but everything is shut down. So I have no current, no temperature.
So you're just flowing electrolyte?
Not even.
Not even, okay. Yeah.
Without even flowing.
No, okay. All right. Yeah, I mean, it seems to me that that's really the crux of the problem, actually, to understand why there is this strong deactivation and solve it, because, yeah. Okay. What about, yes, so one other point, there's also the discussion in the literature about the kind of species that you have adsorbed on the catalyst that depend on the upper potential limit that you have. So these might evolve from being nitrogen type species to OH type species. So did you actually see any effect on the time of recovery and the upper potential limit that you'd actually used when you were doing your polarization curve? There may be a link there that would be worth looking at.
Can you repeat? I didn't really understand.
Yeah, so the kind of species that you're producing, these intermediates that you're producing, and their stickiness, the way they adsorb on the surface of the catalyst, those species are going to be different depending on the upper potential limit that you go to. Okay.
Yes.
In some cases, you're using quite a high voltage.
Yes.
So it may be that your recovery time is also linked to the upper limit that the catalyst actually saw.
I'm not really sure. I mean, I cannot tell 100%, but I'm not really sure because even in the case where I was, for example, here in the case of a commercial catalyst, I don't know. In this case, let's say, let's look at this graph. You can see that I already went very up in the voltage, higher than 1 volt. And when I looked at the recovery time, it was 3 hours for platinum iridium, which is approximately the same value that I obtained with the one that I prepared. But here, if you look at the tests, I was limiting my voltage to well below 1 volt. But I'm not really sure how to define high potential and low potential region, of course. But for me, it was 1 volt because water oxidation and ammonia. But yes, maybe, I don't know. I mean, for me, what I see is that below 1 volt and above 1 volt, it didn't really have an impact on the recovery time. But maybe at 0.7, 0.8, I don't know.
Okay, one other point, and then we have to stop for time reasons. There was also the issue that you had when you were using Soutenance, that you had oxidation also when you went up to quite high concentrations in your catalyst ink. Okay, so this is also something that you kind of put to one side. Did you? I mean, you mentioned that for the membrane of Soutenance that you did the washing to remove the chloride and not chlorine. Chloride, no? Corrected in the thesis. But you don't do that when you use the ionomer.
Yes.
Okay. But I mean, you could do, because you could make your ink and then you could simply flow through electrolyte to wash out the chloride. And this is something that probably you could think about doing.
I already did that, actually. I hope I can find the slide. Actually, here, when I was studying the impact of Soutenance, and you could see that at very high concentrations, we are, if you look at the onset potential, let's say, you can see that for concentrations higher than 15, we have very low potentials which do not correspond to water oxidation. And what I tried to do is that I took this test, where I had 35% weight of the Soutenance in the anode layer, and then I did a specific treatment, which is immersing the MEA in 1 molar KOH, and then I redid the test again, the same one, and then I had a slight increase in the voltage, which could mean that probably we removed more of the chloride that should have been removed, but it wasn't the right conditions, not the right time, maybe we did the longer times. So here I said, okay, let's put this aside. It needs more treatment, more analysis or finding the best conditions to activate the Soutenance without having chloride.
Okay, yeah. One general question then is that given all of the observations that you have and the results of your work, what do you think is the perspective for anion exchange membrane ammonia electrolysis?
What to do to improve? You mean what to do to improve?
No, what to improve? What is the perspective? What are the openings? What is the likelihood that it could actually be used? Is it a credible solution?
I mean, I think we have a problem of catalyst for the moment because the huge recovery wouldn't take us to industrial applications where we need to shut down our electrolysis cell every 3 hours to reactivate the catalyst. So mainly we should work on the catalyst. And me, in my opinion, after all these tests that I did, specifically when I evaluated the homemade catalyst with different active phases, I think that the next step now would be to work on the catalyst support, and in order to find an optimum pore size, I think it could be the solution for the recovery time.
Okay, let's stop there. Thank you very much. Congratulations on all of the work. It's already been said, but there are two very different parts of the thesis. And it's quite rare that we see this kind of work that's actually done in the same document. So congratulations on all of the work.
Thank you.
I'm going to hand over now. Perhaps we'll go all the order down there. Would you hand over to Pedro, please, and then to Christian?
Thank you, Riham. So I have a couple more questions. No, just joking.
I'm done.
Once again, as everybody, I would like to congratulate you for all the work that you did. It's lots of work, and I'd like to congratulate you for the progress that you did and this adventure, this 3-year adventure. I hope you enjoyed, even though it could have been a bit hard sometimes.
It's
So,
normal.
but
It's part of the process.
It's part of the process. It's normal. So I really enjoyed working with you, working over both in the technical economical part, which I master a little bit more, and on the materials, which was new to me too. I will stop here because otherwise you're going to be too late for lunch.
Okay, so thank you very much. I will shift in French because now it's the transition. I heard that you want to stay in France, and
Perfect.
so you have to be more and more accustomed to French. So donc je passe en français.
Déjà, je passe mes autres entières en français, du coup ça va.
C'est très bien. Je remercie aussi donc moi de notre côté le jury pour avoir accepté d'expertiser ce travail. Et puis aussi pour la discussion qu'on a eue aujourd'hui et tous les conseils qu'ils ont donnés, parce que il faut dire que c'était un sujet nouveau pour nous. Le sujet au démarrage, il était très très vaste et très très ouvert. Donc c'était déjà, je pense, très courageux d'avoir accepté ce sujet de thèse et donc de l'avoir mené à bout comme tu l'as fait, parce qu'il y a eu effectivement beaucoup de travail sur un domaine que tu maîtrisais pas au début. Donc vraiment, toutes mes félicitations pour ça aussi. Nous, ça nous a mis le pied à l'étrier. On ne connaissait rien à l'électrolyse alcaline. J'espère qu'on en a appris aussi un peu avec toi et qu'on pourra continuer sur ce sujet-là. Donc, moi, je rejoins Pedro. On a été ravis de travailler avec toi. Tu laisseras un bon souvenir, je pense, au laboratoire. Et puis, on te souhaite maintenant une belle vie dans ce domaine ou un autre en fonction de ce que tu voudras faire.
Merci.
Très bien. Bon, le jury va maintenant se retirer, donc on va discuter. Je ne sais pas si on reste là ou si on se déplace. Oui, d'accord, ok. Bon, Ange, on va se retrouver dans l'autre salle alors sur l'autre lien.
D'accord, je me reconnecte sur l'autre.
Est-ce que Ange est connecté?
Ange, tu nous entends?
Ange, est-ce que tu es connecté? Ok, oui, oui, ça va, donc on avance. Ok, ça, parfait. So I'll continue in English. So Riham, the jury has deliberated, discussed, and the outcome is satisfactory. And you will be a doctor of Université PSL on énergétique et génie des procédés. So there'll be a report at the that we will be preparing, and the content of the report will cover points such as the breadth of the work that you've achieved, going all the way from the techno-economic analysis through materials preparation, testing, and characterization, and the clarity of your presentation, and the quality of the support material that you've prepared, and also some words on your answers to the questions. Congratulations from all of us in the jury.
Thank you.
Thank you. And now there's an official point that now the new procedure is to prêter serment with regard to scientific ethics at the end of the defense of your work. And now that you're a doctor.
En français. I'll try French. en présence de mes pairs parvenus à l'issue de mon doctorat en énergétique et génie des procédés et ayant ainsi pratiqué, dans ma quête du savoir, l'exercice d'une recherche scientifique exigeante en cultivant la rigueur intellectuelle, la réflexivité éthique et dans le respect des principes de l'intégrité scientifique, je m'engage pour ce qui dépendra de moi dans la suite de ma carrière professionnelle, quel qu'en soit le secteur ou le domaine d'activité, à maintenir une conduite intègre dans mon rapport au savoir, mes méthodes et mes résultats. Me now, I would like to thank some people. First, I would like to thank the jury members one by one for taking the time to attend my presentation and to give me valuable insights and feedback. Thank you for all of you for your time. I would like also to express my deepest gratitude to my supervisors, Christian and Pedro, for their unwavering guidance, patience, and encouragement. Thank you for all the time and the effort you had to put for the success of this project. To my friends and colleagues that accompanied me throughout this journey and had to bear me in my ups and downs, I thank you from the heart. Thank you for being here when I needed and for listening to my problems again and again and again. The list is really exhaustive, but I would like to address Ahmad, Jad, Noura, Anael, Lucas. Thank you. Finally, and most importantly, my family. I wouldn't have done it without your support. So lucky to have you. Thank you. And for everyone who's going to be here at 4, you are invited for the pot de thèse. I'm done.
Très bien. Bon. Voilà, donc merci Christian encore et félicitations vraiment à Riham et merci à tout le monde et voilà, bonne fin de soutenance, bon pot et puis à très bientôt, au plaisir de vous revoir les uns les autres.
Au plaisir, Ange. Au revoir.
Au revoir, merci beaucoup. Au revoir.